We would like to give the formal definition of limit. We would like to explain what it means for a function f of x to approach L as x approaches A. And here we suppose that both A and L are finite numbers. So intuitively speaking, when somebody says something like the limit as x tends to 2 of, let's put down a specific function. So 3x squared plus 1 is equal to 13. What this means is that as we plug in numbers that are very, very close to 2 for x, the outputs that we get here are very, very close to 13. And there was a time that people were actually working with limits just by having this understanding without any more rigorous description of what that meant. But this, of course, creates lots of difficulties. Even conceptually, you might argue, well, how much close to 13 should my outputs be before I get convinced that the limit is actually 13? And that question might have different answers for different people. Some people might be convinced by getting 12 and 10 nines, or 13 and 10 zeros. And other people might require 20 or 100 of them. So the formal definition of limit actually achieved in showing that pretty much you have to be able to satisfy everyone. And it was given at a time when Latin symbols and Greek symbols were very popular. So we have two letters that we classically use in this definition. And let's give the definition. So we will say that f of x approaches L as x approaches A, and write limit as x approaches A of f of x is equal to L if for any epsilon greater than 0, there exists a delta greater than 0 such that if x minus A is less than delta and greater than 0, then f of x minus L is less than epsilon. So this is the formal definition of limit, and let's try to understand what it says. So first of all, we should note that epsilon is the really, really small number that should be our starting point, along with the requirement that the outputs of f of x are very, very close to the alleged limit L. So in other words, we give a level of proximity, and we would like to make sure that the outputs of f of x, or the outputs of the function f, are within epsilon of the alleged limit L. And what do we need to get convinced that this is possible? We're given a delta greater than 0, so that if the input lies within delta of the number that we're trying to approach through x's, meaning the number A, then the output satisfies the desired condition, meaning the output is within epsilon of L. Let's try to actually draw this. So imagine that you have a function, and here's the number A that you're trying to approach through inputs, and here's the alleged limit L. And here I should point out that the reason that we have this part on the inequality is because the function may not even be defined at the point A, at the number A. So basically what we're saying is we start with an epsilon, and we're saying that we wish our output to be in here. So this is the number L minus epsilon, and this is the number L plus epsilon. So we want our outputs to be within epsilon of the number L. Then our response to this challenge is to provide with a number delta, to give a number delta, so that if we go from A minus delta to A plus delta, with the possible exception of the number A itself, and that's why we put that x minus h should be less than delta and greater than 0, then for any input chosen in here, the corresponding output falls in the desired interval. If we're able to do that for any epsilon greater than 0, we're able to provide a delta greater than 0 so that this happens, then we accept that the limit of f of x as x approaches A is L. And here we should understand that as epsilon becomes smaller and smaller, delta will also become smaller and smaller. And in a typical application of this definition, usually the kind of application that one does is with a linear function first. So you have to show that, let's say, the limit as x tends to 3 of 3x plus 2 is equal to 11. Then in a typical application of this definition, remember the definition says for any epsilon greater than 0. How can you possibly check the statement that is contained in the definition for any epsilon greater than 0? The key is to fix an epsilon greater than 0 and not reveal it and show that it works. So if we fix epsilon greater than 0, then we state that we wish to find delta greater than 0 such that if x minus 3, remember we're trying to approach 3, is greater than 0 and less than delta, then 3x plus 2, which is the function, minus 11, which is the alleged limit, should be less than epsilon. So in this story, epsilon is given, has been fixed. We don't reveal it because we don't wish to do the job for a specific epsilon and then have to do it for other epsilons. We want to do it once and for all. So the idea is to start with this inequality, analyze it, and understand how small this quantity has to be so that this holds. So hopefully what will happen is the quantity x minus 3 will emerge in that inequality. So that's exactly what happens. So we have 3x plus 2 minus 11 being less than epsilon is equivalent to 3x minus 9 is less than epsilon, which means that 3 times x minus 3 is less than epsilon, which means that 3 times absolute value of x minus 3 is less than epsilon, which is equivalent to x minus 3 is less than epsilon over 3. So this pretty much tells you that how small does x minus 3 have to be so that this holds? It has to be smaller than epsilon over 3. So if we choose delta to be equal to epsilon over 3, then we get that as long as x minus 3 is less than epsilon over 3 and greater than 0, here we could just say less than delta because that's what it is, then 3x plus 2 minus 11 is less than epsilon, which was to be proven, was to be established. And that completes the verification of the definition for this very, very simple case. Now, sometimes people see an argument like this and they think, is there is it something that would prevent us from doing that for any number, not just 11? Because then it seems that it would work for anything. No, it wouldn't work for anything. It's exactly for 11 that the quantity x minus 3 would emerge, and you would be able to isolate it and see how small x minus 3 has to be so as to ensure that 3x plus 2 minus 11 is less than epsilon. And of course, yeah, the limit, if it exists, happens to be unique. Now, this is a very, very simple case. It's not true that you can apply the definition to all cases in such a simple way. But for example, if you work with polynomials, a term of the form x minus a will emerge. You will usually have some other factor that you will need to bound and make the whole quantity less than the desired amount. And that's all. Thanks for watching.